Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 3, Lesson number 4, on the graphical features of functions. Before we begin this lesson, let me remind you that you can find a worksheet and a homework assignment that go along with this video by clicking on the video's description or by visiting our website at www.emathinstruction.com. Also, don't forget about those great QR codes that are at the top of every single worksheet. Use your smartphone or a tablet, scan that code, and it'll bring you right to this video. Alright, let's begin. The graphs of functions have lots and lots of important features, with lots of terminology that you're expected to know. Alright, so we're going to get into some of that terminology today. Some of it will be review from previous lessons that we've had. So let's jump right into it in exercise number 1. Now it says the function y equals f of x is shown graphed below over the interval -7 is less than or equal to x, which is less than or equal to 7. Now just as a side note, when somebody gives you this sort of like notation, what that tells you is that is what the function is defined over. Okay? Those are the values of x that we can put into the function, and we've got nothing outside of -7 to 7. So let's take a look at letter A. Letter A asks us to find the maximum and minimum values of the function and to state the x values where they occur as well. All right. We've talked about maximum and minimum values of functions, so what I'd like you to do is pause the video right now and see if you can figure out what these things are, the maximum and the minimum values of the function. All right, let's go through them. Remember, every time we talk about values of the function, what we're talking about is outputs. Outputs which are the same as the y values. All right? So the maximum y value occurs right up here, and the minimum y value occurs right down here. So I guess we'll start with the maximum because that's the way the problem was worded. The maximum y value is y equals 1, 2, 3, 4, 5, 6, 7 at x equals -1. All right. On the other hand, the minimum, or the lowest y value, is y equals -1 at 1, 2, 3, 4, 5, x equals -5. That doesn't quite look like an x, so I'm going to just get rid of it there. There we go. All right, so whenever we talk about the values of the function, we're talking about y values. Now, something that you should have heard before, especially in terms of lines, is the y-intercept of the of a function, or the y-intercept. Letter B. What is the y-intercept of the function? All right, and then it asks us to explain why a function cannot have more than one y-intercept. Well, the y-intercept is simply the y value where we cross the y-axis. I'm going to color it in red, okay? And maybe I'll circle this in red as well. Ooh, we almost get purple. So the y-intercept is y equals 1, 2, 3, 4, 5, 6. All right. Then it says explain why a function cannot have more than one y-intercept. That's very, very important. Okay. Pause the video for a second and think about why a function, not just a generic graph. You could have a generic graph that has more than one y-intercept. But why the graph of a function cannot have more than one y-intercept? All right, let's talk about it. All right, all capitals, all y-intercepts happen when x equals 0. That's important. Every time you cross the y-intercept, it happens at a place where x is equal to 0. So, if we had, let's say, two y ints, I'm going to just abbreviate it that way, if we had two y-intercepts, then there would be two outputs for, that doesn't look like 4, let's try that again, for an input of x equals 0, right? And as we know, at this point, after quite a few lessons on functions, for every input there can be only one output. So if there were two or more y-intercepts, then there would be more than one output for an input of 0. All right, so only one y-intercept. On the other hand, let's flip that over and let's take a look at C. Give the x-intercepts of the function. These are also known as the zeros of the function because they are where f of x equals 0. So this is actually going to become an important piece of terminology for us, the zeros of a function. The zeros of a function. The zeros of the function are the x-intercepts, and they're where y is equal to 0, right? Let me circle those in green. They're right here and right here. Okay, the x-intercepts are where y is equal to 0, and that occurs at x equals 1, 2, 3, 4, 5, 6, at x equals -6, and at x equals 1, 2, 3, 4, -4. All right, the zeros of a function are where the output of the function is equal to 0. The x values where the output is equal to 0. It's kind of cool. The y-intercept is where the input is equal to 0. The x-intercepts are where the output is equal to 0. And that's why they're called the zeros of the function. Now, no problem with more than one, right? We can have outputs repeat. We can't have inputs repeat for functions. All right, there's a lot written down on this page with a lot of different colors. So pause the video now if you need to, because then I'm going to clear out the text. Okay, here it goes. Let's keep solving problems. Continuing with this one particular function, all right, take a look at what it asks us to do in letter D. Would you characterize the interval x greater than or equal to -5, less than or equal to -1 as increasing or decreasing? Explain your choice. So let's go to x equals -5. 1, 2, 3, 4, 5. Here's -5. And here's -1. So the question is, what's the function doing on this interval? Is it increasing or is it decreasing? All right, now this is important. Very, very important. Okay, is the function increasing or decreasing? Now, for a lot of students, they would say, well, I mean, it depends on which way you're looking at it. If we move this direction, then the function's increasing. And if we move this direction, the function is decreasing, right? So we have to understand how to read a graph. Always read a graph from left to right. All right, now why do we do that? Why do we always read a graph from left to right? And it's very simple. When we read a graph from left to right, then that guarantees that our x values are getting larger. Because implicit in this question really is, as the x values increase, does the function increase or does it decrease? That's what it's always about. Is the function increasing or is the function decreasing? And if we now get rid of this right to left motion, because that's not correct, right? And we go back to always reading it this way, then what we see is that the function increases. So the correct answer is increasing because y gets larger as x gets larger. We go uphill. right? It's a good way to visualize it. As we're moving from left to right, we're moving uphill, okay? Letter E says give, actually it says given, but it should just say give. Give one additional interval over which the function is increasing and one over which it is decreasing, all right? So to give an interval over which the function is increasing, what we want to do is look for another portion where the function is going uphill, okay? And a good example of that is from here to here, right? So from 2 all the way to 3, 4, 5, right? This is x equals 2, x equals 5. From 2 to 5, right, we're traveling uphill. You could also use interval notation really nicely, right? You could go 2 to 5, all right? Likewise, if we're talking about decreasing, then we're looking for a place that we're going downhill. Why don't we use this stretch in here, right? Why don't we use this stretch in here to go downhill? We'll even keep our text in red. So it looks like we're going downhill from -1 less than or equal to x less than or equal to 2. Or interval notation, -1 to 2 brackets. Whether you use brackets or parentheses there is mildly unimportant. All right, those endpoints, is kind of like the bottom of the hill and the top of the hill. All right, if you study calculus later on, which I hope that you all do because it's a great topic, we can either include them or not include them, although in calculus they tend to be included. Okay, so I'm going to clear out the text, pause the video if you need to. All right, let's keep moving. Okay. Keeping with this same function over and over again. Something else some functions have are what are known as turning points. Now our function has 1, 2, 3, 4 turning points, and I think the name says it all. Turning points are also known as vertices. A single turning point could be known as a vertex, all right? But right now we're just calling them turning points. They are the top and the bottom of hills, if you are. They're also known as relative maximums and relative minimums. The reason that we use the word relative is because they are sort of the highest and the lowest points, but only in a certain area. I live in upstate New York and we have the Catskills nearby, and we can talk about sort of the highest and the lowest points of the Catskills, right? And those are the relative highest and lowest points around here. On the other hand, they're certainly not the absolute maximum and absolute minimum points. Those might occur in the Alps or the Andes or other places. I'm probably way off in my geography. I'm a math teacher. Anyway, let's look at each one of these points. Here's our point at -5, -1. Here's our point at -1, 7. Here's a point at 2, 2. And here's a point at 5, 5. What are they? Relative maximums or relative minimums? Circle your choices. Pause the video now, circle some choices, and I bet you're going to get them right. All right. Well, -5, -1 is at the bottom of the hill, right? It's the valley, so it's a minimum, a relative minimum. -1, 7, well, that's at the top of the hill, so it's got to be a relative maximum. 2, 2, bottom of the hill, relative minimum. 5, 5, top of the hill, relative maximum. Not surprising that they alternate back and forth. It's probably hard to even imagine how you could have a graph that doesn't have them alternate, right? Relative max, relative min, relative max, relative min, relative max, relative min, etc. There are possibilities, but they require a graph to become what's known as discontinuous. All right, and we're not going there. Not quite yet. I think that actually completes exercise number 1. I'm going to clear this out, so write down what you need to, and then we're going to move on. All right, all clear. Let's keep going. to our piecewise functions. Oof, okay, fair enough. Remember, piecewise functions, and this one's known as a piecewise linear function because both of these are equations of lines. We'll get into those more later on in the course. But piecewise linear functions are simply rules that are given or that are created by combining two or more smaller rules, if you will. Okay? Remember the way that we interpret this, and I'll go with different colors here. Let's start off with red, is that I'm going to use the formula x plus 3 anytime x is less than or equal to 1. So, wow, that's like all of these, right? And then I'm going to use the rule 6 minus 2x anytime x is greater than or equal to 1. That's weird that I included 1 in both of them. Maybe that's a typo. Or maybe it's not. Anyway, we'll put a little star here, and we'll come back to that. So let's start doing some calculation. Okay, so we got to use x plus 3 anytime x is less than or equal to 1. So we'll get negative 4 plus 3. That'll be negative 1, and we'll have the coordinate point negative 4, negative 1. Likewise, when I have negative 3, I'll get negative 3 plus 3, which is 0, giving me the coordinate point negative 3, 0. Negative 2 plus 3 gives me positive 1, giving me the point negative 2, comma 1. Negative 1 plus 3 gives me positive 2. That gives me negative 1, comma 2. 0 plus 3 gives me 3. 0, comma 3. Now let's use it anyway. I mean, it says it's valid. 1 plus 3, which is 4. So I'm going to leave a little bit of room. 1 comma 4. Okay, now the other rule kicks in. If you don't mind, I'm going to kind of work this rule backwards because I want to leave that x equals 1 for last. All right, so remember, here we're going to do 6 minus 2 times the input. Now remember, that multiplication has to come first, right? So that's going to be 6 minus 8. And that's going to be negative 2. So we have the point 4 comma negative 2. Then we'll have 6 minus 2 times 3. Again, the multiplication has to come first. So 2 times 3 is 6. 6 minus 6 is 0. Right? Then we'll have 6 minus 2 times 2, which is 6 minus 4, which is 2. And let's see what happens when we apply that rule when x is 1. Here we'll have 6 minus 2 times 1, which is 6 minus 2, which is 4. So we'll get the point 1 comma 4. Look at that, same point. Now the reason that I did this in this exercise, because again, at the cutoff point, those two outputs are the same. Okay, so there's nothing wrong with that. Okay, what would have been a problem, what would have been a huge mathematical mistake on my part, the person who's designed this worksheet, is if those two y values came out to be different. If one of them had been 4 and one of them had been 5, we would have had a serious problem on our hands. That wouldn't have been correct. All right, so let's do some graphing. All right, negative 4 comma negative 1, I'll go in red. Negative 3 comma 0. Negative 2 comma 1. Negative 1 comma 2. 0 comma 3. 1 comma 4. I could have put that one in blue as well. I think I'll switch to blue. 1 comma 4 we already have. Again, same point. 2 comma 2. 3 comma 0. And 4 comma negative 2. All right, let me connect them up. Yeah, I'm already in red. So I thought I was in red. Problem is I hadn't switched over to my line application. All right, and maybe a little arrow because it'll go forever that direction. And let me go here. And again, nice little arrow. And there's our piecewise function. Love it, right? Now, what we're going to do though is we're going to move on. You're going to have that table and that graph, and what I'm going to do is I'm going to reproduce the graph for us so that we can then talk about the graphical features of this particular function as we work through the problem. So I have to clear this out just because of the way my software works. So write down anything you need to. All right, here we go. All cleared. Let's keep going. Now what I've done is I've put the graph up here. I did it all in red. That's okay. Letter B asks me to state the zeros of the function. Now we introduced that idea previously. See if you remember what that means, or look back at the front side of the sheet. Pause the video now and see if you can answer both B and C. All right, let's go through them. Remember, the zeros of the function are the places where y is equal to 0. That's right here and right here. That happens to be x equals 1, 2, 3, negative 3, and x equals 1, 2, 3, positive 3. All right, there are our zeros. The function's y-intercept, that isn't too bad. Wow, I have a lot of 3's here, don't I? I'm a big fan of 3 in this problem. Y equals 3. All right. Now let's talk about increasing, decreasing. This could be confusing, especially because of the arrows we've put on our graph. But remember, even though I might have this arrow here and this arrow here, I will always read the graph in this direction. So it says give the interval over which the function is increasing, give the interval over which the function is decreasing. Well, the function is going to be increasing all along here, right? So in fact, it's going to increase from negative infinity, can't put an equal sign there, less than or equal to 1. Whether you put that equal there or not doesn't really matter. In interval notation, negative infinity to 1, I'll kind of keep the bracket there. It's decreasing from 1 out to infinity. Again, whether you have the equals there or strictly a greater than, less than symbol doesn't matter. In interval notation, 1 to infinity. Love the interval notation for these things. Consider using that, right? Where you start, where you stop, brackets, parentheses. All right? Letter E. Give the coordinates of the one turning point and classify it as either a relative maximum or a relative minimum. Why don't you go ahead and pause the video and see if you can answer E on your own. All right, let's go through it. Well, there is only one turning point. Let me mark it in green. Actually, let me erase some of this. All right, now we'll, whoops, go back to green. There's my one turning point. It's got coordinates of 1, 1, 2, 3, 4. So 1, 4. And that is a relative maximum. All right, letter F. Use your graph to find all solutions to the equation f of x equals 2. Illustrate your solution graphically and find evidence in the table you created, a table which we unfortunately don't have the screen on anymore and would be hard to have the screen. But you've got the table on your own paper, so hopefully you can look at that, or you can, of course, rewind the video if you need to. Now, remember, here what we're given is we're given an output. Sorry that this is all the way on the bottom of the screen, but we're given an output of y equals 2, and what we really want to find is what the x values are, okay? So you know what I'm going to do? I'm going to actually draw in a nice black line right at y equals 2. Well, or at least I'm going to try to make it at y equals 2. That was a little bit too high for it. Sorry about that. Right, whoops. Now I'm going to get rid of that line. All right. Right here is one place where the output is 2, and here's another place the output is 2. So solving that equation gives me x equals negative 1 and x equals positive 2. All right? So that's tricky. When given an output, when we're trying to find inputs, that's a much harder task, a much, much harder task. Finally, letter G asks us to state the interval over which this function is positive. How can you tell this quickly from the graph? All right, now I know that there's a lot kind of drawn up on that graph right now, but I need to erase it because I need to be able to explain this important topic to you. All right, now notice what the thing says, right? It says state the interval over which this function is positive. I'm going to highlight this now. This function is positive. Okay? Very, very important. All right. The function is the y values. Now, just think a little bit. Going to the graph. Here's a y value that's positive, right? But here's a y value that's negative. Here's a y value that's positive. Here's a y value that's negative. In fact, all the y values up here are positive, and all the y values down here are negative. So, the place where the function is actually, we'll go blue, is actually positive is everywhere in here. Everywhere where it's above the x-axis, right? This is where it's positive. It starts being positive, not at -3, but very close to -3, right? And then it ends being positive at x equals +3. Now, we cannot include the equals there. We cannot include the equals there because it's not above the x-axis. It's at the x-axis, right? Those are its zeros. But we cannot include the -3 and the 3 because it's not positive there. Interval notation here, I think, is great. -3 to 3. Of course, the most problem part of interval notation is the fact that this kind of looks like a coordinate point, but it's not. It just means that the function is positive, starting at this value, ending at that value, but not including them. Okay? Very important. We can always tell that a function is positive. Get that out of my way. We can always tell that a function is positive where it's above the x-axis and negative where it's below. But what's interesting is that we give the x values that give us positive y values. And we give x values that also give us negative y values if we're asked where the function is negative. All right, a lot on this page. I'm going to clear it out. So pause the video now and write down anything you need to. All right, it's gone. Let's finish up the lesson. Today we introduced a lot of important function terminology, some of which are things like the y-intercept, the x-intercepts, also known as the zeros of the function. All right. We also introduced the idea of a function increasing over a particular interval of x, a function decreasing over a particular interval of x, right? We talked about relative maximums and minimums and how they relate to this idea of a turning point. And finally, we also saw where functions were positive and where functions were negative. So, we're going to be using that terminology a lot in the future. Make sure that you watch this video or talk to your teacher as much as you need to understand these terms. Thank you, though, for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kurt Weiler, and until next time, keep thinking and keep solving problems.